Okay, I think that Teams is recording. Just to make sure, yeah, it is recording. Awesome. Yeah, this is the second time I teach over Teams. The first time was this morning at 9:30 for another class. I normally teach over online using Collaborate or Zoom or something else, but we're not using Collaborate anymore, and we don't have Zoom capacities anymore. So we do have Teams, and that's what I'm going to be using. When I was uploading the videos for a couple of weeks ago, I noticed that I had some issues with the recording of the precipitation video, and I wasn't able to upload it. I know that is something we covered 2 weeks ago, but at least, even though we're not going to cover precipitation as a whole, I want to at least give a brief summary of precipitation since the video of it was not uploaded. Okay, so let's just start today's class by reviewing precipitation a little bit, and then we'll continue the class by talking about runoff, which is actually the topic of this week. Right. So starting with precipitation, in order to understand precipitation as a function within the hydrologic system or within the hydrologic cycle, we do need to understand how water eventually works overall in the hydrologic cycle. That way we can understand precipitation. So a couple of weeks ago, we did talk a little bit about water balance. So let's review that a little bit. Water balance is the concept of water being, a real substance and conservation of mass being applied to that water so that, we actually comply with the law of conservation of mass, which says that matter cannot be created nor destroyed. So we talked a little bit about that. We wrote down the differential form of the conservation of mass equation, but we also said that we could actually simplify that into this nice little integral form, which says that the difference in inflow and outflow for a control volume is going to be equal to the change of volume of that control volume. Now, you don't really have to understand this equation mathematically. As long as you understand it conceptually, I think you'll have the tools needed to actually use the water balance equation. If you're curious, the differential form of this equation was something like this. And again, don't be scared by all the weird symbols. I know we've dealt with this in fluids before, but the important thing is to know that these two things are actually saying more or less the same thing, right? Water is incompressible, therefore this term goes to 0. This density can be taken out of this term, and in the end, we can end up with the divergence of velocity being equal to 0. Again, as long as you understand it conceptually, you don't really need to worry too much about the math part. Conceptually speaking, all we're saying is that if we were to study a control volume, let's say that this is our control volume, and we were to add water to that control volume, we can add water at a rate of Qn. And then we can say we can take out some water from that volume at a rate of Q out. If the rate at which you're adding water and the rate at which you're taking out water are exactly the same, so Q in and Q out are exactly the same, does the amount of water inside the container actually change if you're putting in the same amount that you're taking out?
No.
It doesn't, right? Which means that if Q in and Q out are the same, this becomes 0. And that makes sense, right? You can tell the volume doesn't change, so the change in volume is 0. If Q in is greater than Q out, then you know that the volume is actually increasing. And you can see it here, right? If Q in is greater than Q out, this will be a number greater than 0, which means that my volume is increasing. And if Q out is greater than Q in, that means that the volume inside the container is decreasing. And you can see that if Q out is greater than Q in, then this will be a negative number, which means that the volume is decreasing. So the general idea of water balance is to understand that water is essentially, it is a fluid, and we treat it with the same laws that we would treat any other fluid. So the law of conservation of mass being one of them. So I did want to review that. I want to make sure that at least there's one video that has that, because we will turn back to this equation eventually. When it comes to nomenclature, we do use some different terms here in hydrology. So typically, we don't really use dV over dt. Instead, we talk about that in terms of the change in storage with respect to time. But we don't really use dV over dt. We use S. instead of volume. And S really means storage. So whenever you see an S in a hydrology equation, remember, all we're talking about is the volume. Okay, so we do use S for volume. And finally, the water balance equation really consists of us trying to figure out what are all of the things that contribute to Q in and what are all the things that contribute to Q out. We call it a water balance equation, but don't really think of the equation in terms of these are the variables that need to be there, because different systems are going to have different sources of inflow and different sources of outflow, right? And I think we talked a little bit about that in the last class. We did say, you know, for this control volume, what can be possible sources of inflow? Well, I think all of you mentioned precipitation was one of them. Right? You have clouds, it rains, that rain falls into our control volume, so precipitation is one of the sources of inflow. And because it's inflow, we are going to give it a positive value, right? We talked about other sources of inflow as well, right? We said that if there's a stream or a river, and that river passes through our control volume, then of course there's going to be a flow coming in from that river. And we can call it inflow, we can call it stream flow, you can call it whatever you want. We also said that if there's some groundwater that's flowing, you know, inside, but under the ground, but can still seep into your control volume, then we do have that as well. So we have groundwater inflow. And look, this is all very conceptual, right? That doesn't mean that we have these three variables and these three will always be your sources of inflow. It just means that, well, this is what we have so far, okay, in our control volume. What about outflow, right? Does anybody remember any of the sources of outflow that we discussed? Like what possible things can take water away from my control volume?
Evaporation.
Evaporation, right? And because evaporation is a form of outflow, we're going to give it a negative sign. We also had transpiration or evapotranspiration. We also had infiltration. So we can set our control volume to be, or to consist of whatever's on the surface and maybe whatever's at 1 feet below the surface. But eventually, things will continue to infiltrate. And that can also be a cause of outflow. And of course, we do have stream flow. So all the runoff that travels through the control volume eventually is going to leave, either through a stream or through a common drainage point. So I can call this just drainage. Now, according to this equation, all this is equal to the change in storage. Now, these can be viewed as flow rates, in other words, volume over time. Or if we want to make this equation simpler, we don't have to look at it in terms of volume over time. We can look at it as just volumes, right? We can multiply everything by the amount of time that it takes to run our simulation and say these are just volumes. And that means this should be equal to the change of storage in our control volume. We're going to deal with this equation a lot throughout the rest of the class. My purpose here is not to give a second class on precipitation. It is just to maybe summarize these basic terms. Now, when we talk about precipitation, we did say that precipitation could be measured at certain points, but we'd have to expand that measurement over areas. And that's where we can go towards the first workshop we did in this class, where we actually interpolated to find some values of precipitation. Now, in the first workshop that we did, which we weren't able to record, everything that you interpolated actually ended up giving you the same results, right? Or very, very similar results. Now that's good because that means that your interpolation was correct. That also means that our assumption that precipitation varied linearly across space was also a good assumption for that particular project, the particular project that we're working on for the semester project. But now today, we are going to have a short class on what happens after precipitation, right? So as far as the hydrologic cycle goes, we have our nice control volume. I can draw it maybe in the form of a hill. I'll draw some trees to make this nice, maybe a little house. We have precipitation that lands on our control volume. And what happens to the water, let's say, after it lands at this point, what possible things can happen to a drop of water after it lands on the ground?
It can infiltrate.
Okay, so it can either infiltrate or what else?
Run down the hill.
Yep, it can infiltrate or run off. Okay. The amount of water that infiltrates, we're just going to call it infiltration, or the process of infiltrating, we'll call it infiltration. And the process of running off, we'll just call it runoff. Focus of today's class is on looking at ways we can calculate that runoff. It's important that I mention infiltration because you'll see that runoff and infiltration are directly related. Therefore, we can't have one without the other, all right? Or we can determine one without the other. Any water that doesn't really infiltrate into the ground or that doesn't evaporate very quickly is eventually going to run off into the outfall or the next stream or the next water body. We typically call this water rainfall excess. So the amount of water that doesn't infiltrate is called rainfall excess. I'm going to move my camera a little bit. There we go. So rainfall excess is water that doesn't infiltrate or evaporate quickly. Now, you may be familiarized with the timescales of evaporation, but even if you're not that familiarized, I think we can understand it a little bit conceptually. You know, it rains, you know, let's say it rains for about an hour. And some of the water from that rain pools into this nice little area. Let's say we have a nice little low point here. Maybe we had a pipe here, but the pipe got clogged up. So now all the water just pools up here. Water can infiltrate. Yes, we know that. Or it can evaporate. Now, here's my question. If the rainfall event lasts 1 hour, so it takes 1 hour, we have 1 hour of rain, okay? Do you think the evaporation, do you think all this water that accumulated here, the one that didn't infiltrate, do you think it's gonna evaporate also in the scale of about an hour, or do you think it'll be more, or do you think it'll be less? Like, how long do you think the evaporation is compared to the duration of the rainfall?
Evaporation takes longer than the amount of time it takes for rainfall.
That's right? Evaporation takes much, much longer than rainfall. In other words, rain can actually fill up this low point a lot faster than it would take to evaporate this low point. So we're going to start with making one interesting assumption here. We are going to assume that at low time scale, at small time scales, evaporation is negligible. So we're assuming that at small time scales, typically the time it takes for rain to fall down, maybe a day after that, evaporation is going to be negligible. And what that means is that we can actually now calculate the runoff with a very simple equation. We know that it's going to rain some amount P. Let's call the precipitation P. And we know that that water is going to be either infiltration, I can call that capital I, or runoff, I can call that Q. So we have precipitation, infiltration, and runoff. We can use this equation now to solve for runoff. We can say that runoff is going to be equal to how much it rained minus how much infiltrated. If you want to have a very accurate equation, accurate to the 7th decimal point, then you're also gonna want to include evaporation here. But because we can assume that evaporation is negligible in small timescales, then for small timescales, runoff can be seen as precipitation minus infiltration. We already know that we can measure precipitation from measurements, from data. So what's left is to calculate, or better yet, estimate infiltration. So we can get precipitation measurements, and you already know how to find the precipitation and how to interpolate to find precipitation at a specific point in your study area. All we have to do now is to find the infiltration. Because if we can find the infiltration, we can find how much water was infiltrated, then we know how much water actually runs off, how much excess rainfall we have. And I want that to be the focus of today's class. In your workshops, you are going to calculate or measure different properties of your watershed, and you're going to do so in order to estimate that runoff. But you're going to estimate that runoff in a very mechanical way, and you're just going to push buttons and measure quantities. I want you to understand what's happening during that measurement as well. Like, how are we actually calculating or estimating this amount of infiltration? So we can agree that runoff is simply the difference between precipitation and infiltration. What rains, so what falls into our watershed, minus what gets infiltrated. That should be our runoff. In order to determine infiltration, then we have to ask ourselves, well, what factors affect infiltration? So I'm going to ask you to give me some ideas on what factors affect infiltration. Any ideas? So what parameters do we need to take into account to estimate the infiltration?
Permeability of the soil.
Okay, soil permeability, good.
How much it's rained recently.
How much it's rained recently, and that's really important, right? So maybe a little history of rainfall. And I have a question. That's actually a parameter that not many students come up with. What do you think, how much it's rained recently? What do you think that information is relevant in our calculation of infiltration?
Well, because if it's rained a lot recently, then the ground's already full of water, and
Exactly.
And there's no more room for the water to go in.
Exactly. So we can know what the porosity of the soil is. We can know what the permeability is. We can know how much water the soil can absorb, but that actually doesn't help us unless we know how much water the soil has right now. Right? In other words, the history of rainfall in that soil is going to end up influencing how much water can actually infiltrate into the soil. Can you think of any other properties? And let me give you a conceptual example. Let's say we're looking at two columns of soil. They have their own porosity, but they're made of the same material. So these two columns are made of the same material, okay? The only thing that changes is the geometry of the columns, but they have the same area, they have the same materials, and let's say they have the same initial water content. If we make it rain the same amount of water on each two columns, which one do you think will infiltrate more water?
The rectangular one.
Exactly, and why is that?
Because you're sloped on the trapezoidal one.
Exactly, right? The slope on the trapezoidal one is going to result in more runoff. More water is going to run off because the slope increases its velocity, and of course, it needs to take some time. It takes some time for water to actually infiltrate. If you pass through the watershed really quickly, you're not going to have time to infiltrate. So that's absolutely right, Seth. The one with the flatter slope is going to result in more infiltration. So slope is one other property we're going to have to take into account. And that's all very, very, very good. We'll learn of other properties. There's actually many, many different factors that affect infiltration, and we're going to look at them in detail as we work through the workshop. But at least I wanted to get you to think on what are the factors that influence infiltration. The most important factor for this class is going to be the soil type for us, because different types of soils will have different permeabilities, different porosities, different and just different hydraulic capacities. Now, it's actually very hard for me to define infiltration in a very rigorous manner without going into the details of groundwater flow. And I just saw a comment in the chat, which was water table, and that's correct. That's another thing that influences infiltration. That's absolutely right. So there are a lot of factors that infiltrate, and I mean, we could take today and spend the entire day deriving some pretty awesome groundwater flow equations. However, this is not really a groundwater flow class, and groundwater flow is not within the context or scope of this class. It should be, but it's not. Therefore, we do need to find a simpler way, I would say, to try to estimate infiltration. So we are going to derive some basic governing equations, but we're not going to derive them very rigorously. Instead, we are going to look at other methodologies that we use to determine or estimate infiltration. Before we start using these other methodologies, which in this class we're going to focus on Horton's equation, before we start on Horton's equation, I do want to at least show you what the governing equation looks like, just so that you have an idea of what you'd be dealing with when you're working with groundwater flow. Essentially, if we take Darcy's law for flow through a porous medium, which I've done the derivation in some graduate courses, it's essentially a law that considers liquid flow through a bunch of tiny, tiny, tiny circular tubes. And we use that equation to approximate flow through a porous medium. And when I say porous, well, obviously I mean a solid that has holes in them, pores, through which water can travel. Applying Newton's second law of motion, or specifically Navier-Stokes equations, into these little tubes, we get Darcy's law. I'm not going to write it here, it's a little bit long. And if we combine Darcy's law with the continuity equation, which, if you remember correctly, continuity equation is simply conservation of mass, which says that matter cannot be created and destroyed, we can actually arrive at what's called Richard's equation. So Darcy's law plus the continuity equation allows us to arrive at Richard's equation. Richard's equation is a general equation that gives us the infiltration capacity of a soil as a function of the hydraulic conductivity of that soil. Hydraulic conductivity is simply a value that tells me how much water can actually travel through the soil, and that value is in length over time. I'll explain the dimensions in just a second. Now, don't be scared of all these partial derivatives and all these ordinary differential equations. We're actually not going to solve Richard's equation in this class. Instead, I want to explain what these terms mean. You probably recognize some of these terms from the continuity equation. You can see that this is simply the density change over time. However, this is not really density. This is going to be water content. So we can look at a column of soil, and we can say, within this column, how much water is there in that soil? So we take that water content, which would be the volume of water divided over the volume of the column, and then we derive it over time to get the density change. So remember, this is not really density in terms of mass over volume. It's more of a water density or water fraction in terms of volume over volume. So this is units of 1 over time. We have the hydraulic conductivity, and what we're saying here is the following. We are saying that the water content changes with elevation. So if we look at Z, we know that as we move through Z, the water content will change. And what we are saying here is that the hydraulic conductivity will also change as you move through Z. Okay. So the whole point of this equation is to say, is to try to figure out how much water can the soil absorb based on how much water it has and what is the gradient of water that it has. In other words, what's the difference in the amount of water content up here when compared to the amount of water content down here. Just so that you get a bit of an idea why we care about the location of the amount of water content, different water contents will result in different pressures, and different pressures or pressure gradients will eventually influence or cause things to flow. If you took my fluids class, then you know that I always like to define movement of fluids as kind of like a pressure differential. If there's a difference in pressures, then the fluid has to be moving. And that's exactly what we are going to be looking at here. The difference in pressures will result in fluid moving. But of course, you can see that this equation may not have too many exact solutions. In fact, this equation only has exact solutions for very, very specific types, similar to the Navier-Stokes equation, which we solved some exact solutions last semester. But we can solve it numerically. Now, to reiterate, the purpose of this class is not to derive Richard's equation or to solve Richard's equation, but I want you to at least understand the following. I want you to understand that the water content in a soil column is going to change with depth. And because the water content changes with depth, then the conductivity, the amount of water, the speed of water traveling through the soil will also change with depth. So if we have some amount of water traveling at one velocity, so entering the soil at one velocity, that's not going to be the same velocity down here. The velocity actually changes with depth as well. So if we can keep those concepts in mind, it will make understanding these next equations a little bit easier. So that's all we're going to see in this class for Richard's equation. Again, don't worry too much about it. Now let's go to the model that I actually would like for you to learn for this class. In 1939, Horton presented a model of infiltration that is widely used, even to this day. There are a lot of different models for infiltration, and some of them are more popular than others for specific types of projects, for specific types of scenarios. My purpose in this class is not to say, hey, these are every single models that you can use. Instead, I'm going to give you this one model, this main model, which is a pretty good one. And from there, you can figure out which other derived models you can use based on how you simplify your project. The Horton model assumes that infiltration is a function of 3 different parameters. In order to talk about those parameters, let me show you what the Horton model says infiltration is like. The Horton model, you'll see, depends a lot on measurements, okay? In other words, we need to have already measured some infiltration values before we use it. Now let's explain what these means. F sub P in the Horton model is essentially the infiltration capacity, okay? So F sub P is the capacity of infiltration. In other words, what the Horton model is telling us is how much water can the soil infiltrate. And notice that it's a function of time. So what this is really telling us is how much water can the soil infiltrate at a particular point in time. The units of F sub P are length over time, usually inches per hour. And the reason they are length over time, even though you have volume of water infiltrating, the reason we do length over time is so that we can apply this model to a unit area, right? So the area is 1. So if we're applying this model to a unit area, so volume over time divided by unit area, just length over time, then all we need to do later is to figure out what the area of your watershed or your control volume is, and then just multiply this by the area. So we use the Horton model in terms of unit area just because it's easier for us to apply it into a full watershed. F naught is what we call the initial infiltration capacity. or initial capacity of infiltration. In other words, at time t equals 0, at the very beginning of a rainfall, how much infiltration capacity did the soil have? As you can see, this depends a lot on experiments, right? Because we need to know what the initial infiltration capacity is to determine what the infiltration capacity is after some time. So at time equals 0, maybe this soil column has some initial capacity. Of course, that initial capacity has to do a lot, not just with porosity, but with how much rainfall had fallen in recent times, okay? And finally, F sub C is what we call the final infiltration capacity. So what does final infiltration capacity mean? It doesn't mean, the capacity at the end of your rainfall. It just means once this soil is saturated. And when I say saturated, what I mean is that all the pores in this soil are filled with water. It has as much water, right, as it could have. Once it is saturated, what is the infiltration capacity? It still has some infiltration capacity because air pockets can be rearranged, but the capacity should be different from the initial infiltration capacity. Now, I'm going to ask some conceptual questions. I just want to make sure that we understand this at a conceptual level. Do you think the initial capacity of infiltration is greater than or smaller than the final capacity of infiltration? In other words, before it starts to rain, which is the initial capacity, do I have more infiltration capacity or less infiltration capacity than after my soil is saturated? What do you think?
You have less after your soil is saturated.
That's correct. And Ruth says, yeah, we have more at the beginning. So more at the beginning, less at the end. So I think we understand this concept. If we can understand it conceptually, we should be good, right? We can tell that the initial capacity will be always higher than the final capacity. You don't increase your capacity by adding water to the soil, right? You actually decrease your capacity when you add water to the soil. Finally, we have a constant K. And K is simply a rate of decrease in capacity, which is just a constant and would be determined empirically. Our variable then becomes time. So we can use this Horton model to estimate, okay, the infiltration capacity at different times in our model. The Horton model is very popular. It's very simple to use. It does require a bit of calculations, but it doesn't require, going the numerical route, right, or solving differential equations. It's actually a relatively simple model that we can use by making some assumptions. Model is what I would like to focus on in this class. And in order to make sure we understand it, I do want to make sure that we can come up or solve a simple runoff problem using the Horton model. Now, this is just capacity of infiltration. But I mentioned earlier that runoff was just precipitation minus infiltration. So all this gives us is the capacity for I. How do we actually go and calculate the runoff? Well, there's a very simple equation. The runoff, which I'm going to write down as RO to match the nomenclature of the book, is going to be equal to the rainfall intensity. This is rainfall intensity, so related to precipitation, times the amount of time it rains, minus the change in accumulated water. We'll talk about how to calculate this in a second, minus the change in available storage. Now we're going to talk a little bit about how to calculate all these different values. The important thing in this equation is to know that runoff is precipitation minus infiltration. And of course, we do need to consider changes in storage because our watershed can actually have changes in storage over time. What this means is if you were to have, for example, a little watershed that looks like this, and you have water raining in this area, we already know that some of it is going to infiltrate and the rest is going to run off. However, some water can actually accumulate here. It may also infiltrate, but not all of it may infiltrate. And then once it gets full, water can then run off. So what we're saying here is that the total runoff, the total amount of water that actually leaves my watershed, let me make this a little bit brighter. The total water that leaves my watershed is going to be equal to how much it rains minus how much is infiltrated minus how much is stored in the watershed. So we're just adding the extra term. We're not going to look at it in this example, but I did want to make it clear that sometimes we can have storage and we can use storage as a way to reduce the amount of runoff because the water can be stored there for some time until it infiltrates or until it evaporates. Then we don't have to worry about it when it comes to calculating our runoff. I'd like to take the rest of the class to solve example 4.1. Now, I don't want to solve it and just have you look at me solving it. I do want you to solve it with me because this example has a lot of steps. It is somewhat complicated. Once we actually solve it, it will become easy in your eyes, but I think you actually have to solve it first in order to understand it. So try to solve the example with me. As a bit of an analogy, I know you don't like analogies and you don't like me sharing my life with you, but as a bit of an analogy, I do have students in my fluids class that just take photos of the board. And I understand if I'm going too fast, then of course, then you got to take a photo, but which is why I usually ask students to just let me know when they're done so I can move on to the next topic. If you don't really practice the problems yourselves, for those of you that speak foreign languages, you kind of know, right? Like not solving problems is like trying to learn a foreign language by listening and not speaking, right? You can listen all you want, but if you don't actually practice speaking, you're not going to learn a foreign language. And I know that a lot of us speak more than one language here, so I think you understand what I'm trying to get at. So let's try to practice this problem ourselves. Let's try to see if we can actually solve it together. The book does have a solution to this problem, but I'll be honest, it takes a bit to understand that solution. So I think it's better if we just solve it ourselves just now, okay, without actually looking at the solution. So this is going to be example 4.1 of your textbook. You can look it up if you need. In this example, we are given a watershed with an infiltration capacity of the following. Now, before we move on and talk about how to solve this problem, I just want to make sure that we understand what each of these terms actually mean, right? So F sub P, remember, that's the infiltration capacity. At time T. This 11.66 represents the initial infiltration value. Remember, we talked about the initial capacity of infiltration. This 0.83 represents the final capacity. And this 0.07 is our constant that shows how capacity changes with time. Okay, just make sure we understand all these terms. Now, this is the infiltration capacity of our watershed. It depends on the soil in our watershed, and we already have some measured values that tell us what the capacity is at the beginning of the event and what the capacity would be once it is fully saturated. Now, let's make it rain. Let's say that we have rainfall given by the following intensity curve. We have time in minutes, and we have intensity in inches per hour. The intensity curve will be as follows, from 0 to about 10 minutes. We're going to have an intensity of 3.5. and we're given intensity values in intervals of 10. Okay, before we move on, let's also talk a little bit about the units. Remember that infiltration capacity is length over time. In this case, it'll be inches per hour. And initial capacity and final capacity also have to be inches per hour. So let's just make sure that we understand. Time here, however, is given in minutes. So I want to make sure that we know the units because we will have to do some unit conversions here. Okay. So these are the properties of the soil. These are the properties of the watershed, and this is what's raining, what's happening to that watershed. So all this rain is falling into a watershed with this infiltration capacity. Now for this problem, I would like to determine what the runoff is, or the rainfall excess is, right? For 10-minute periods, right? For these 10-minute periods. So determine the rainfall excess. Okay. We have how much is raining, and we have how much is infiltrating. Conceptually speaking, our runoff should be equal to how much it rained minus how much it infiltrated. However, you know that it's not going to be that simple. Okay, we're going to have to make some changes to convert this and this into units that we can actually solve for. All right, so let's take some time. I want to take some time for you to write down all this, and let's make sure that we're all ready to start working on the problem. So before I start, just you can write in the chat when you are ready to begin. And take your time. We're not really in a hurry. This is the only example I want to do in the class because I want to work on it in detail, in a lot of detail. Okay. So when you're ready to start, you can just let me know in the chat. All right, good. Seems like we have a good number of students that are ready to begin. So let's start solving this problem. We're going to use the Horton model, the Horton infiltration method, in order to solve this problem. There's a lot of steps, so bear with me, and let's just work on these steps together. What I like to do to solve this problem, and I think it is the best way, is to create tables. That just helps me keep track of all of my calculations a little bit easier. So I'm going to write down a table with the different time intervals that our precipitation provides. So I'm going to start with my time, and this is in minutes. Now, instead of writing intervals, I'll just write the first and the last point. So 0, leave some room in between, okay? 10, 20, 30, 40, 50, 60, and 70. Try to leave some room in between your intervals because we will need to do some stuff in between these values, okay? So we start by creating a table. And in that table, we're going to include all our different time intervals. The reason I'm dividing this into intervals of 10 is because those are the intervals that my precipitation table or precipitation curve gives me. Okay, so these time intervals are going to depend on what precipitation data you have available. If my precipitation data is in intervals of 10, then I'm going to have intervals of 10 here as well, right? Then for each time period, I'm going to compute the infiltration capacity. And here's the important part. The reason I'm not writing intervals here, I'm just writing actual time values, is because this infiltration capacity equation is at one point in time. So I'm going to have to find the infiltration at each point in time, not for a range of time, okay? So I'm going to calculate F sub P. Remember, this is inches per hour for each time period. How do I calculate F sub P? Well, I can plug in each time value into this equation and then get the results. Of course, at this point, you may be thinking, well, this may actually be a little bit easier to write down in Excel. So if you do want to write down this in Excel, it will just make your life a little bit easier, and mine as well. Take your time and work on that. In the meantime, I'll be calculating these values with my calculator just to confirm that they match the values from the book. Okay. Now we have a problem here, and Ruth kind of understands it, right? Ruth says, well, should we divide T over 60? Okay. For this particular problem, we don't have to. We would, yes, we would, because this is inches per hour. But in this problem, we don't have to, because this constant is already taking into account the unit conversion, which means that this time is going to be already in minutes. So very, very good catch, very, very good observation. It's not necessary for this particular problem, just because in the equation, this constant is already taking into account the unit conversion. But again, very, very good that you pointed that out, because not all equations are going to do that, okay? So in this case, time is already in minutes, so you don't have to worry about making any unit conversions yet. And your answer will end up being in inches per hour based on this constant. This constant kind of makes that conversion for you, okay? All right, so let's start calculating these infiltration capacity values. I would say we can kind of share the load a little bit. So perhaps I can calculate for time equals 0, because it's the easiest one. And then you can pick a random time and then calculate it. And then once you have that number, just let us know what you got, and we can confirm or check if the value is correct. All right, so take your time and work on this. We still have more than enough time to finish this project, so to finish this problem. So just take your time and work on this and let me know what you get for the infiltration capacities. In the meantime, I'll get my calculator and also try to get some values myself. Obviously, I picked the easier value. I'm going to solve time equals 0 just because we don't really need a calculator, but you can see it here. When time equals 0, e to the 0 is 1, so 1166 minus 0.83 plus 0.83. It should be just 11.66. Okay, maybe I can get a different value as well. So I can actually put in some work here. Let's see, for time equals 10, what do I have? I'll calculate 10 first. All right, so we have about 6.21. We're going to round that up for time equals 10. Okay. Everybody have for time equals 20, and I do have a confirmation for that value from Ruth. Right? We can try the same thing for time equals 20. Ruth has 3.5. All right. What did we get for 30? Okay, 2.16. Awesome, 2.16. And you can just write down whatever value you calculated. All right, 1.49. For 50. And then for 60. Okay, and then for 70. Perfect, thank you. All right. We have put together our little time interval table, and we have calculated the infiltration capacity for each of these times. Good. Remember, precipitation, this is an intensity that occurs over a time interval. So that doesn't mean that at time 0, it rains this much and then it stops raining until time 10. No, over the course of this time, we have this amount of precipitation. So let's determine what the interval of times are. This will come in handy later. So delta t is simply the interval of time. So from 0 to 10, we have an interval of 10 minutes. From 10 to 20, we have an interval of 10, and so on and so forth. Now, this may seem like a bit redundant for you right now. However, our precipitation data will not always be in these nice uniform intervals. Okay? And that's why it's important to know what the interval of time is in between each value for which you measured the infiltration capacity, or for which you calculate the infiltration capacity. So these are just intervals. So this 10 is in between 0 and 10. This is 10 minutes in between 10 and 20, 10 minutes in between 20 and 30, and so on and so forth. Again, remember, these intervals are not always going to be very uniform. So you may just want to write them down now so that when you try to solve a different problem, you'll be able to use them as needed. Now we have a problem here. We have this much infiltration at 0, at time equals 0, and then over the course of 10 minutes, the infiltration reduces from 11.66 to 6.21. How can we figure out what the total amount of infiltrated water will be? I think one thing we can do is try to figure out how the infiltration changes from 11.66 to 6.21. And here we can go to our little idea of integrals, which we talked about in a previous class. Remember we mentioned that integral over the curve is just the area of the curve. If I want to know how much volume was infiltrated and I have two different infiltration rates, one thing I could assume is that the infiltration rate is constant, and that constant is equal to the average of the beginning and the final rates. What that tells me is that the infiltration rate changes linearly. If you're not too sure about that, let me just put it this way. We have an infiltration rate, F sub P. We have another infiltration rate. Oh, I guess it should be lower. We have a lower infiltration rate, F sub P. So at time 0, we have this infiltration rate. At time 10, we have this infiltration rate. If we assume that the infiltration changes linearly, we know that the total volume of water infiltrated is the area under this curve, because this is length over time, this is time, so this will be a length, but it's obviously per unit area. And this is actually the same as taking the average, FP average, and assuming that the average acts across the entire time interval. We'll still get the same amount of area. What that means is that I'm going to assume that for this interval of 10 minutes, the infiltration is actually going to be equal to the average infiltration. All right. So for each interval, I can calculate my average infiltration. Does that make sense so far? Average infiltration and why we're using it. Just to make sure we're on the same page. What do you think? Do we understand why we're using the average infiltration instead of the individual infiltration values?
Yes.
Yes.
Okay, awesome. In that case, let's find those average values. Over the course of these 10 minutes, my infiltration goes from 11 to 6. I'm just going to assume that over the course of these 10 minutes, my infiltration was just the average of those two values. So the average of 6.21 and 11.66 is just 8.94. And you can find averages, by just adding these up and then dividing by 2. Okay. The average of 6.21 and 350 is 4.86. And I'll give you time to calculate the other averages, and you can just let me know as you calculate them so that I can write them down here. Right, do you have some averages you want to share with me? I'd like to know what the averages are for the remaining intervals.
The next one is 2.83. And then 1.82. And then 1.32. And 1.07. And 0.95. And I guess the last one, because you don't really have another value to average it with, it would just be 0.91.
Well, we don't really need anything beyond this, right? Because this is the interval, and this is where the interval ends. So there's no need to average anything else after that. So yeah, that's pretty much it. These are our intervals these are our average infiltration capacities for these time intervals. Good. We're getting somewhere, don't worry. Why am I doing this? In the end, I want to know how much volume was actually infiltrated, which means that at each time interval, I'm saying for this 10-minute interval, we have however much water infiltrating. I'm going to call this infiltrated water, just the infiltrated water, I guess. That's a nice name. Remember, infiltration is a volume. The reason we are writing it in inches is because we're wanting to express everything in terms of unit area. So volume over area is a length. So I would like to know, over the course of these 10 minutes, this much can be infiltrated, right? How much total volume was infiltrated? So how do we find that? Well, we know what the capacity is, length over time, and we have the duration of that infiltration time. So we want to end up with length. So what do we have to do with these two terms in order to get the amount of infiltrated volume? Any ideas? And you can actually just look at the units and then tell me what we have to do. In fact, just think of it. Yeah, go ahead.
Multiply them?
Yeah, we multiply them. We multiply time times length over time, and we end up with a length. Good. Now we have a problem here. This is inches per hour. This is minutes. So what else do we have to do in order to make sure that our units are inches?
Divided by 60.
Correct. Good. So we get, and I'm going to try to write down the equation here so you can see it. We get that the infiltrated volume is going to be equal to the amount of time multiplied by the average infiltration rate. But this is minutes, this is inches per hour. So we need to make sure that we make the correct conversions. Okay. And how do we make the correct conversions? Well, we know that there are 60 minutes in 1 hour. And that should give us the amount of infiltrated water. Okay. So 10 times 8.94 is 89.4. All we have to do now is divide that by 60. In the interest of time, yeah, go ahead.
1.49.
Thank you.
And then 0.81, 0.47, 0.3, 0.22, 0.18, 0.16, and then 0.15.
There's nothing after 0.16, right? Because there's no interval after 0.95, right? Remember, I think someone had originally said 0.91 afterwards, but there's nothing after 0.95, right? 0.95 is the last time interval. After that, our rainfall ends, all right? So let's just leave it at these numbers, okay? Very good, very good. And finally, I want to know what my cumulative infiltration is. So how much is actually infiltrated? And this is fine. This is just a cumulative value. So I have 1.49. And at the next interval, I'll have 1.49 plus 0.81. So that's 2.30. Right? 2.30 plus 0.47 is 2.77. 2.77 plus 0.30 is 3.07. 3.07 plus 0.22 is 3.29. 3.29 plus 0.18 is 3.47. And finally, 3.47 plus 0.16 is 3.65. So this is how much water has infiltrated or could infiltrate across these 70 minutes of rainfall. Now, the purpose of this problem was not to find how much water was infiltrated. In fact, unless you're dealing with groundwater flow, the purpose of the problem will never be how much water infiltrates, right? You don't really care about how much water infiltrates. What you want to know, right, is how much runoff we have. And that's actually what the purpose of the problem is. We calculated how much water had infiltrated because we know that runoff is rainfall minus infiltration. Now, we actually have a problem here. Now that we calculate all this, we could say, well, let's figure out how much rain actually falls over these 70 minutes and then subtract this value, and we have, we have our runoff. However, it's not really that simple, because if we try this calculation, we're going to end up with some negative values, or we're going to end up with some values that just don't make sense. And I'll explain why. This gives me the infiltration capacity, okay? And notice that this has nothing to do with the rainfall, right? Everything we've done so far is only following the properties of the soil itself. So this is not really how much water was infiltrated. This actually tells me how much water the soil could infiltrate. But the rainfall itself is going to determine if that's the case or not. It could rain less than this amount, in which case the amount infiltrated will be less. It could rain at different intensities, and with those different intensities, we can have a different relationship here. So now that we've put together our little Horton table, we are going to have to make some adjustments to this table, and those adjustments are going to have to consider the actual rainfall. So let's talk a little bit about what those adjustments will be. First off, we need to figure out how much rainfall is fully infiltrated. And we can actually see this visually by looking at the tables themselves. Over the first 10 minutes, it rains 3.5 inches per hour. Over the first 10 minutes, we have an infiltration capacity of 8.94 inches per hour. Based on this, how much of this rainfall is infiltrated during the first 10 minutes of rain? And I see in the value 3.63. Yeah, it should be 63. Didn't add. Yes, 6 plus 7 is 13. Yep, 3.63. Thank you for the correction in the chat. So now let's answer this question then. Over the first 10 minutes, it rains 3.5 inches per hour, and I have the capacity to infiltrate 8.94 inches per hour. So how much of the rainfall is infiltrated during those 10 minutes? I see in the chat a 5.44, but then my question is, how can you infiltrate 5.44 if only 3.5 actually rains? Right? Remember conservation of mass, matter cannot be created nor destroyed. Let's see if we can understand this visually. I have my watershed, it's this container. I have the ability to let out 8.94 inches per hour. So I have a hole big enough to let out 8.94 inches per hour. But now, how much I add 3.5 inches per hour. I can let out 8.94, but I'm only adding 3.5. So how much water is actually being infiltrated?
3.5.
Exactly, 3.5, which is everything, right? We have the ability to infiltrate 8.94, which means that any value less than 8.94 during this 10 minutes is going to be infiltrated. You throw 3.5 here, we're going to have 3.5 out the other way. So remember, this is the capacity. Capacity means what's the most you can do. If we have less than 8.94, that means that all of the rainfall will be infiltrated during those 10 minutes. Okay? So we know that for the first 10 minutes, all the rainfall is infiltrated. For the next 10-minute period, we are raining, we have about 3 inches per hour, and we have a capacity of 4.86. So how much of that rain for the next 10 minutes is being infiltrated?
3.
3, which means all of it, right? Good. So all of it here is infiltrated as well. For the next 10 minutes, we have 8.0 inches per hour and a capacity of only 2.83. So conceptual question, is all the rainfall being infiltrated or not?
No.
Right? Correct. It isn't infiltrated because we have more rain than what we can actually infiltrate, which means that only for the first 20 minutes is all the rainfall infiltrated. And we're going to have to make some adjustments to our equation and to our table to account for this. Because for the first minutes, all of it is infiltrated, which means that our infiltration capacity really only becomes an issue after 20 minutes. Before 20 minutes, it's okay because we're infiltrating everything. After 20 minutes, that is when we need to consider our infiltration capacity. I don't think we'll have time to finish this problem, but I want to go out cover as much as we can before class ends. But don't feel worried if we don't finish it. We'll have some time on Thursday to wrap up the problem. Once we figure out how much is actually infiltrated, we need to ask ourselves, how much volume does this actually provide? Okay, so we have infiltrated this amount of water. I want to know how much volume we actually infiltrated. So now we look only at the rainfall to answer the question of how much volume is infiltrated. We know that over the first 20 minutes, this amount of intensity was infiltrated. So how can we turn this into a volume? Well, intensity is inches per hour. Perhaps to turn that into a volume, we need to multiply by time so we can get into a length. Remember, this is all unit area terms. So that volume that was infiltrated is going to be 3.5 inches per hour over the course of the first 10 minutes. And of course, I'm going to have to make a conversion here. I'm going to convert from minutes to hours. So in 1 hour, we have 60 minutes. So that this cancels out and this cancels out. That's for the first 10 minutes. Plus, for the next 10 minutes, help me out. What would I have to multiply to determine how much volume was actually infiltrated? And you can follow the same style here. This is the first 10 minutes. Now I want for the next 10 minutes, for 10 to 20.
Wouldn't it just be 3 would be the only change?
Exactly. Correct. Correct. 3 inches per hour, right? Over the course of 10 minutes. And then our conversion factor. We plug this into our calculator. We should get about 1.08 inches. So we get that over the course of these first 20 minutes, we have already infiltrated 1.08 inches of water. And that's important to know. Because remember, we have a limited capacity of how much water we can infiltrate. Okay? So we're going to have to take these 1.08 inches of water that we have already infiltrated and then adjust this table based on this value. But we're going to leave that for Thursday. We're going to take the first 10 minutes of Thursday to wrap up this problem before we work on the workshop and do the quiz. Yeah, I will see you on Thursday.